Today, we're going to talk about the silent crisis that could bring the whole AI revolution to a grinding halt. And you know what? It's not about faster chips or bigger data sets. It's about the one thing we all take for granted: power.
So, if I asked you what's holding back AI, your mind probably jumps to things like faster processors or maybe bigger AI models, right? But what if the real bottleneck, the thing that's truly slowing us down, is something way more fundamental?
Yep, you're looking at it. The single biggest challenge for AI right now isn't the silicon, it's the power cord. It all comes down to the ability to deliver, convert, and, most importantly, govern power efficiently. As these AI systems get more and more powerful, they are hitting a very, very real power wall. So what's the solution? Well, in this explainer, we're going to break it all down. First, we'll unpack this hidden power crisis that AI is facing. Then, you'll meet the Power Governor, a really cool new technology built to tackle this problem head-on. We'll dive into its strategy for keeping the power on no matter what, peek inside its two-part AI brain, and see how this whole thing scales from a tiny little chip all the way up to the power grid.
Okay, let's get right to the heart of it. As we keep cramming more and more computational muscle into smaller spaces for AI, we're generating an incredible amount of heat. Power consumption isn't just some line item on an electric bill anymore. It is the #1 physical constraint. It impacts everything from raw performance to how long the hardware itself will even last.
For decades, we've relied on these standards. You've probably seen the little 80+ sticker on a power supply. It's supposed to promise a certain level of energy efficiency. But here's the catch. That standard was made for a totally different era of technology. And when it comes to the way modern AI systems use power, it has some absolutely massive blind spots.
This table just lays it all out so clearly. The old 80+ standard, it only measures efficiency at a few fixed, steady points. But AI workloads, they are anything but steady. They have these huge blind spots for what's called light load behavior, when a system is mostly idle, and for transients, which are these sudden, massive spikes in power demand. This new approach, regime-aware governance, is totally different. It's designed to manage power continuously across all of those wildly different conditions.
So if the old way is broken, what's the fix? Well, let me introduce you to a new piece of tech called the XRPMC. It's from a company called H-Chip, and it's not another power supply. No, it's a dedicated power governor built specifically for our most demanding systems.
Honestly, the easiest way to wrap your head around the XRPMC is to think of it like a highly intelligent traffic cop, but for electricity. Its job isn't to create the power. Its job is to manage the flow perfectly, keeping everything stable and efficient no matter how crazy the traffic gets.
And you can see right here where it fits into the whole system. The XRPMC, right there in the middle, it's a digital governance layer. It doesn't replace the core power components, the transformers, the converters, all that stuff is still there. Instead, it acts as the brain, intelligently managing the entire power path, collecting data, and making smart decisions in real time.
Okay, so one of the governor's most critical jobs is to make sure the power is never, ever interrupted. I mean, even a millisecond-long glitch can bring a multi-million-dollar AI workload crashing down. So how does it guarantee that continuity?
The key is this concept called ride-through, or RT for short. You can think of it like a tiny, super-fast, uninterruptible power supply, a micro UPS that lives right on the circuit board. It's an energy buffer that instantly kicks in to fill any gaps or absorb any glitches in the power supply. And the power of this little buffer is, well, it's staggering. This chart shows the raw data, but let me give you the key takeaway. A tiny onboard energy buffer, one that's measured in a unit of storage called farads, can let a system handle a massive, totally unexpected power spike for a critical half-second. So just how big of a spike are we talking about?
278 watts. That's nearly 4 times the system's normal operating power. It can handle this massive short-term demand without crashing, all thanks to that ride-through buffer. This is the kind of safety net that these modern systems absolutely need.
And the process itself is just elegantly simple. A power dip, or a spike, triggers the system. The ride-through buffer immediately kicks in to hold the power stable. And this gives the main system time to adjust or switch power sources before it can safely exit the ride-through state and get back to normal operation. Trigger, hold, exit. It's simple, safe, and incredibly effective.
But this power governor is way more than just a simple switch. It has this sophisticated 2-part AI brain that combines hard physical rules with adaptive learning. It makes it a truly intelligent system.
Let's see how that works. Okay, on one side, you've got the algorithmic guardrails. Just think of these as the unbreakable laws of physics for the power system. These are hard safety limits that can never, ever be broken. Then, on the other side, you have the machine learning optimization. This is like the expert driver that operates within those safety guardrails. And this combination is what's so brilliant. It means the system can constantly learn and adapt to improve efficiency and even predict failures before they happen, all without ever putting the hardware at risk. You really get the best of both worlds, deterministic safety and adaptive intelligence.
So we've got this incredibly smart chip, but the vision here is so much bigger than just one little component. The real power comes from its ability to scale up and impact entire infrastructures. And the solution is designed to scale beautifully. It starts right at the A1 mainboard level, governing power for just a single device. From there, it can be integrated directly into the A2 power supply unit itself. Then it scales up to the A3 backplane, managing power for a whole server rack. And finally, it can manage power all the way up at an A4 grid node. It's one single, coherent strategy from the smallest piece of hardware to the biggest infrastructure.
And the development roadmap is just as smart. Phase 1 uses something called an FPGA, which is basically a flexible, reprogrammable chip, to test and validate the technology across all kinds of different applications. Once the design is proven solid, it moves to Phase 2, creating an ASIC. And that's a powerful, cost-effective chip that's custom-built for this one job and ready for mass production. It's a really low-risk, high-reward strategy.
And this final diagram, well, it brings everything we've talked about together. You can see the interfaces across the top for inputs and outputs. That's where it handles things like fault isolation and load sharing. But the real magic is right there in the middle, that central control and governance plane. That's the brain of the whole operation, using real-time data and policies to deliver stable, efficient, and truly intelligent power. Look, this isn't just some technical curiosity. It's a fundamental shift in how we need to think about computing. It brings us right back to where we started. As the source material says, the game has completely changed. The limiting factor is no longer just raw computing power. It's about the intelligence of the power systems that support it. So I'll leave you with this final thought. As we race to build these ever smarter AIs, maybe the most important question we should be asking ourselves is this one. If we're going to give our AI a smarter brain, shouldn't we start by giving it a smarter power cord?